The other reminder is the gymnosperm assignment is due Wednesday. Wednesday. By 9 p.m., not midnight, 9 p.m. Okay. So now we're getting into the second slide set on the angiosperms. And so today we're going to look a little bit at monocot versus dicot, a little bit about the evolution of the flower. And then after this slide set, we'll get into flowers and fruits. The flowers and fruits are looking at pollination strategies, fruit dispersal, fruit anatomy, those types of things, okay? But today we're going to look at flowers, monocot versus dicot, and then evolution. Also, fair warning, I've been up for the last 2 nights with a very sick dog, so I'm a little sleep deprived, and so if I say something wrong, please kindly correct me, and hopefully I can muddle through this. So, okay. This is just a different perspective on the life cycle, different figure. It's not from your book. So if this helps you as you're studying, it's kind of got both the male and the female structures and what's going on in each. And then I put the embryo sac or megagametophyte development on the left there. So that's another study tool. Okay, so looking at the evolution of, when you look at the angiosperm, definitely we now see this partnership, this co-evolution between the plant and its pollinator. And we'll talk about the different pollinators. I'm sure you're familiar with most of them. But when you look at the evolutionary process, they suspect beetles were really the first active pollinators to transfer pollen from the male part of the flower over to a stigma, the female part. And then once flying insects evolved, that really allows for greater spread of pollen, of course, and the pollination mechanism. And so that was a huge advantage as well for the angiosperms to have that kind of partnership with these special flying pollinators. So then we're going to talk a little bit more in more detail in the next slide set, but we're going to be thinking about, well, how are plants managing to form these partnerships with these pollinators? And sometimes it has a lot to do with reward. You know, you want to reward the pollinator, but not always. There are some plant species that deceive their pollinators and are really good at it. A lot of orchids are like that. They're fascinating in their ability to deceive the pollinators. Poor things. Then sometimes odors come into play, but not always. And so I'm sure you smell pretty flowers, at least to your nose. You say, oh, that's very pleasant. Some flowers are not so pleasant to our nose, but are very attractive to their pollinators, the pollinators. And then we're going to look also at how do they go about seed dispersal. There's different strategies. Sometimes they will form partnerships with dispersers, certain animals that can do that, but not always. Sometimes it's a very, well, actually, I'll show you some video later this week on explosive seed dispersal mechanisms that are quite amazing, and a lot of physics involved in that in order to get their seeds to just spread really far from the mother plant. So when you look at angiosperm, so that coevolution with their pollinator they point to that as a huge reason for why angiosperms dominate planet Earth, is that they have that kind of system in place. But don't forget just about their inherent, you know, what they're born with idea. Like they're born with very tough leaves for the most part. They have xylem and phloem that allow for the flow of water and minerals and nutrients. Their seed coat, you know, first of all, just developing a seed rather than having a spore for dispersal, they have the seed for dispersal. That's huge. And then a really tough seed coat, so seeds can stay viable for long stretches of time. They also point to the idea that many of the angiosperms trees are deciduous in the sense that they drop their leaves And they think that's a pretty good adaptive strategy because then they can just go dormant through a really tough time. So they don't have to try to exert all those energy, the resources of energy to survive winter. They can just go ahead and take all the nutrients out of their leaves, tuck it away for the winter, drop their leaves, and go to sleep, so to speak. And so that's a good strategy for many angiosperms. And then we'll talk more about how they have evolved these mechanisms for pollination and seed dispersal. And of course, angiosperms are being heavily studied for all the chemicals that they can produce. Those secondary metabolites we've mentioned here and there in this class. So those secondary metabolites are really important for them to defend themselves primarily. That's the main reason why they make so many of these secondary metabolites, is that if they're getting attacked by bacteria or fungus or herbivore, that they can try to defend themselves. So here is an image of a phylogenetic tree, and they have on here different spots of when certain things are showing up. And you can see with the, we're going to talk a little bit more about some of these concepts, not all of them, but some of them. And so, you see the spot for 2 cotyledons, pollen with 1 opening, loss of 1 cotyledon. All right, so they've been able to track quite a bit of these traits over the fossil record and looking at the different angiosperms. And then the so-called basal angiosperms are the ones that are lower down, closer to the root of the tree. They're more ancient. And then you have the more evolutionary advanced Dicots that translates into the true dicots. And so sometimes they're referred to, we just say dicots, but you really want to be super precise, you would say Dicot. So we're going to look at some of these, and actually this next table kind of takes some of those, what we saw on that previous slide, and puts it into table form. And so you can see what they're looking at in terms of characterizing the different angiosperms. They look at flower design, they look at pollen, does it have 1 or 3 openings going on the seed, or leaves in the seed, vein pattern, vascular bundle pattern, split system. So these are common characteristics that they're using to classify the different angiosperms and try to fit them onto a phylogenetic tree to show how they went through the evolutionary process, how they're related to each other or distantly related to each other. So this is a good table to look at when you're studying. And then some of the subsequent slides here are going to be kind of fleshing out some of these concepts a little bit. So let's see, dicots. When you look at angiosperm, after you say, oh yeah, it's like a flowering plant, then the next thing you ask yourself is it a monocot or is it a dicot? That's the next kind of classification scheme. If you suspect it's an angiosperm dicot, then what you're looking for is 2 cotyledons, which are in the seed. Remember, they're often referred to as embryonic leaves because they're actually in the seed. When you crack open the seed, see 2 cotyledons. And then when you look at the flower parts, they're typically in parts of or multiples of 4 or 5. So this flower that you see on this image, if you count the flower petals, that's usually the easiest way to do it. Count the flower petals. As you see here, there's 5 flower petals and 5 stamen. So that would be a clue that it's most likely a dicot. The other thing, if you have to guess, and if someone says, hey, is that a monocot or dicot? And if you don't know, you're just going to guess dicot, because 80% of all angiosperms are dicots, right? So they win. They're more abundant. So trees and shrubs, and then many, many herbaceous species fit into this dicot category. So 80%, and then 20% roughly are the monocots. Dicots also have that netted leaf vein pattern, where the veins run in all sorts of directions with respect to each other. And then the pollen, when you look at those under the microscope, they should have 3 pores or apertures. And if that's the case, yep, it's a dicot. Yes. 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 Yeah, you'd have to look under the microscope for sure. Monocots compared to that, one cotyledon. And usually the flower parts are in multiples of 3. Look for that pattern. And again, the easiest way to do that is to look at the flower petals. Although sometimes, depending on the flower design, that can get a little confusing. So a lot of herbaceous plants, some non-woody trees, like some palm trees, Joshua trees, they don't have true wood in their stem or trunk. Parallel veins in the leaves. So the veins should all run pretty much parallel with each other. And just one aperture or pore in the pollen grain. So please spend some time thinking about these traits of what makes a monocot versus what makes a dicot. And it's a good rule of thumb. They hold pretty firm. This is another nice comparison with some nice visual. Down here, I like that they also included the roots and the stem. So going back to that table, they also talk about that too, like what's going on with their vascular tissue. With monocots, we have that scattering of the vascular tissue in the stem, and they don't form any true wood stem. And then with the dicots, they have that ring of vascular tissue, and they can form many dicots, true wood in their stem. And then monocots tend to have more of a fibrous root system, where most of the roots are about the same size. And then many dicots, not 100%, but many dicots tend to have this central taproot that's a little bit bigger, more prominent, and then they'll have a bunch of lateral roots as well that are usually smaller. Okay, so this is a good table. This is another one. If you want to look at that one. So these are the characteristics that they're looking at. Like if someone discovered a new plant and needed to figure out what it is, this is what they would be looking at more carefully with that plant. So following the fossil record, they, many of the primitive angiosperms, we've been able to see good fossils, but it's a challenging task. I don't envy the people who do this type of research. It's very, boy, they really have to do a lot of searching and a lot of painstaking work. So what they've been able to piece together is that when you look at more primitive plants that evolved, that are closer to the root of the tree, so to speak, they have these primitive features where their flower parts are many flower parts. So here you see on the top image, lots and lots of stamens, just tons of them, lots of stamens here, numerous petals. They're all kind of separate. There's no fusion of flower parts there. It's all like really separate and just lots of parts. That's a characteristic of more primitive flowers. We also say that they're radially symmetrical. That means when you look at it and if you were to cut it in half, doesn't matter which way you cut it, you will get a mirror image of the two halves. Take that slice in half. So they're radially symmetrical. And I think you can kind of get the idea here that the ovary, the female part of the flower, is buried here, and it's sitting on top of where you see the stamen attached, on top of the petal attached. So you have a superior ovary. That's another really kind of a dead giveaway that you have a more primitive flower. And then if you compare that to advanced flowers, well, we tend to see over time through the evolutionary record with studying the fossils, as you get to more advanced plants, you start to see less flower parts. They reduce the flower parts. They tend to fuse, at least some of the flower parts tend to get fused with each other. And so You can get compound pistils with part of the fusion process. That's a good example. And then they tend to be bilateral in their symmetry. So if you cut that flower in half, there's only one way to do it in order to get mirror images. So right down this image, you have to cut straight down from the image top to bottom for the two halves to be mirror. So we're bilateral as well. Humans are bilateral. And then as you walk through the fossil record, you tend to see, more ancient plants have that superior ovary, and then gradually the ovary starts to embed deeper into flower tissue until it's inferior with the more advanced flowers. So this top flower here is a magnolia flower from a magnolia tree. And we have some magnolia trees here in town that are, there's one in 7th Street Cemetery. I heard, oh, there used to be one at the Upper Harbor. I think they might have chopped that one down, unfortunately. But here, I'm trying to show that we have lots and lots of stamen, lots and lots of pistils, lots of petals. Everything's kind of all separated. And then the ovary, hard to see here, the ovary is superior. And then the orchid on the right, and to see that fusion of the petals and other parts. Often the stamen is fused as well to the female part. And then very much an inferior ovary. Okay. Here's the idea again of ovary position. The more ancient flowers have a superior ovary. And then as you work through the fossil record to more current flowers, they go semi-inferior and then inferior. And then here's the idea of radial symmetry. Any way you cut that yellow flower on the left, you'll get mirror images. Or bilateral, right, with the orchid. There's only one way to cut that one. So that's the general trend that we see through the fossil record. And then when you look at flowers and look at the flower tissue, there's been a lot of debate on what tissue did the flower originate from. Most botanists would say that they're modified leaves. A few say it's possible they could have been modified stem tissue, and then kind of like a fusion of some stem tissue, some leaf tissue. But I think the first bullet point is holding sway in this day and age. More people are thinking that it's modified leaf tissue. Some say that the petals might have actually come from the stamen of the flower that shifted and evolved into a mechanism to be more flashy. So, stamens in general are pretty petite and small and easy to miss visually. And so they think, well, maybe some of the petal design actually came from stamens that kind of morphed into the petal so that the overall flower could look more flashy to attract pollinators. So there's that idea out there too. And then petal fusion. We often see with the more advanced flowers that they'll have like they call it a corolla, tubular corolla, a fancy way to say it. That if they say that, what they're implying is that there's been fusion, so that it looks almost like a trumpet design. And often you'll get the stamens fusing along with that. So it depends on who you talk to, how they're gonna think through this, but here are some visual ideas on how you might have seen the process of getting anthers to develop, where initially they say it was on a leaf in more primitive plants. And then as the evolutionary process and, adaptation to the environment and trying to attract pollinators and all of that, you start to see this reduction in the leaf tissue and kind of making the anther more prominent and a little bit more upright on that filament, up on the stalk, the filament. Yeah.
Are they more ancient or I'm blanking on the flower?
Yeah, so the fact that they have lots of parts to them, you know, there's that aspect where you think they're a little bit more ancient. They're actually, though, a very large group of plants. The Asteraceae family is big. Yeah, it's a big group. And I'll show the anatomy a little bit more of the those types of flowers. They're really cool looking. And really, we're talking more in when you look at those flowers, it's an inflorescence. It's actually many, many flowers all grouped together. So,
So, so
yeah, yeah. When you look at how many. So the stigma style and ovary, they're showing on the bottom row there that you had again lots of leaf tissue involved initially, and then you start to see this kind of rolling infusion of the leaf, and then the stigma's kind of on the seam of the leaf. And then you start to see reduction in the leaf tissue. So it really is the, the style and ovary is really the remnants of what the leaf tissue was. Stigma right up on top. So lots of ideas out there. These are accepted, widely accepted ideas on how the male and female structure of the flower might have evolved over time. And again, they're showing fossil evidence for a lot of these ideas. Okay, so these ideas of inflorescence, please get those committed to memory. Perfect is implying that you got everything. You got the male, you got the female, it's all there. So Angiosperm is the male, Dicot is the female. Imperfect, that means it's either a male flower or it's a female. And then an inflorescence is a group of flowers clustered together in such a way that it looks like one flower, but it's really many flowers. Okay. I'm not going to get into the anatomy of inflorescences. This image is just to show you the diversity of inflorescences, but I'm not going to ask you about what's a raceme versus a panicle. I'm not going to do that. This is more just to get you to think about the diversity. And then you may have noticed on some trees around here, some trees, in the spring, before the leaf out, you'll have these things dangling from the tree branches. Those are actually flowers, believe it or not. Catkins, flowers that look like that, and can shed lots of pollen from there. But you can see that there's lots of designs from very, very simple catkins to very complex and beautiful inflorescences. And so if you are out hiking around and you're trying to identify certain angiosperms, the field guide that you have with you, they'll walk you through this. They'll ask you to look, is it a panicle type inflorescence or umbel? So they'll use those terminology. So if you'll need to learn that if you ever do an identification out in the field. So the two largest families of the angiosperms are, believe it or not, the Orchidaceae, the orchids, which is weird if you live in this area of the world because we don't see many orchids here at all. And then the Asteraceae is another huge family. And they have those inflorescences. So the Asteraceae have clusters of what we call disc flowers that are more in the center of the flower, and then the ray flowers around the perimeter. And often when you look at the ray flowers more carefully, they tend to be either female or they could actually be sterile. There's no sexual substance. And then if you can follow that flower's pollination events all the way to seed formation, they tend to, and well, even with the flower, getting the flower bud to mature and bud open on that inflorescence, you tend to see the spiraling pattern of how those little tiny flowers will bud open. And also when they get pollinated, that tends to happen as well. And then you'll start to see the seed formation or the fruit formation in a definite spiral pattern. So if you can grow some sunflowers or something like that in your garden and you have some good pollinators coming along, that's always fun to watch. So the flower is being dissected on the left image. And so you can see the ray flower, in this case, sunflower, the female, has the single style and ovary, and then the petal. And then they're also showing disc flowers. So with the disc flower, it's a perfect, those are perfect flowers. And so you have the stigma, style, and ovary, and then the anthers are fused to that. They're essentially fused to the style. And so you have both male, female, and those tiny little disc flowers. So it's very easy when you look at the sunflower. Very easy to understand why you would say, oh, look at that flower, like it's a flower. But in reality, it's many, many, many flowers all compacted together. So what happens is you'll start to see a spiral pattern of the flower body open. You'll actually see that too. When the sunflower seeds start to emerge, you'll start to see that spiral pattern as well. If you can watch it through the summer. So that's a dissected actual sunflower, and you can see how packed together they all are, and all these tiny flowers. Orchidaceae, like I said, is the largest family, which is just, it's hard for me to remember that because I just don't see that many orchids around here. And all the orchids you see here are terrestrial. They are in the forest floor. You know, they grow from the forest floor. They're not epiphytes growing on branches of other trees. So you have to go very much south of here, tropical, subtropical. I think I may have mentioned already that their seeds are really unusual because they're dust-like insides. They're just tiny, tiny little seeds. It's really kind of a puzzle of how little they devote to the seed. And when you look at orchid flowers, they're probably one of the most ornate and diversified flower type out there. They vary in their morphology tremendously. And a lot of it has to do with human intervention, with breeding and tissue culture groups. But when you look at a typical orchid, what you see are three petals. One is called the lip. It's usually modified to allow for the pollinator to have easy access to where it needs to go. And then there'll be two wing flowers. And then there'll be the three sepals behind that. So remember, the sepals are the when you look at a flower bud and it's all green, you know, the flower bud's all closed off and you see those green leaf-like structures, those are the sepals. So what happens with the orchid when the sepals fall open, there'll tend to be three of those, and then it reveals those two wings, one flip-like petals. And again, remember they have bilateral symmetry, so there's only one way to cut them in half for mirror images. Some orchids are what we say saprophytic in the sense that they, especially the seeds, the baby orchid as it's growing, it has to get its nutrition from some other organic matter near it. And they typically won't even germinate unless the fungus, the correct fungal species, is right there associating with the seed and helping to feed that baby sporophyte inside the seed. So if you don't have that fungus, the seeds won't germinate. It's a very specific pairing. Not any old fungus will do. It's very, very specific. Here are anatomy. We have the two petals on the left and right, off the middle, and then this more colorful looking design. That's the third cup-like or lip-like petal. And then the three behind it are the sepals. They're not pretty, they tend to color as the petal color. So that's another unusual thing. Now that's kind of like the standard anatomy, but again, it's very tremendously orchid species. The other thing too is you tend to see fusion, where you have the male and the female parts. They tend to get together. They're not separate in the flower. And so these images here are showing some very bizarre looking orchids. And if you look at them closely, they might remind you of other things. So that top left, that one, doesn't that look like a duck in flight? It's called a duck orchid. The one here, the top middle, it's called the Dracula or vampire orchid. And then that looks like a dove tucked away in its nest, perhaps. That's a dove orchid. Monkey orchid in the lower left. Isn't that amazing? Egret. That looks like a flying egret bird. This one, they call it the naked man orchid. So that, there's I can't remember the term, but there is a term for when things in nature look like something else. There's a special term for that. But like I said, orchid flowers can be pretty bizarre, pretty ornate. Both. I think some have, if you, and I have yet to do this, I got to get down to the Chicago area right around spring break time. I think that's when they do their big orchid. Oh my goodness. Yeah. And they just have, is that the time of the year where they have just all kinds of orchid vendors, like set up these huge, like the size of the dome or something, and it's like, oh boy, if you bring a credit card, you're in trouble. And so a lot of what they have on display has been through human intervention with how they're breeding, and there's a lot of manipulation. Yeah. But I think some of these are natural too. I can't remember how much, like percentages, I don't know. But one of my former grad students, Scott, he was a lover of orchids, and when he finished his master's here, he went back to Minneapolis area and he worked initially until he got his real job. He worked in a greenhouse, an orchid greenhouse, where they would sell orchids. And he was telling me when he came up here to visit that they had one customer that was like pumping so much money into that business because he was really wealthy person, he had a huge mansion, and he insisted that every room in the house, including the bathrooms, have blooming orchids all the time. And so they would sell him orchids in bloom. He put them throughout the house. And then the other really cool thing about orchid flowers is they last so long. I mean, months. I have some in bloom in my house right now, and they'll probably last most of the summer. For months, they'll last for months. And then once they drop their leaves, though, then they look more boring, so to speak. And it takes a long time for them to flower again. So then that guy would send all of those back or donate them and say, I want another batch. So, like, wow. I mean, that person was clearly way into orchids. That's a lot of cash flow he's expecting. So it can get a little wild. Orchid mania, I guess, can be a thing. It's an obsession. Some people say that word too. And they're a really fascinating group. I've tried to not get obsessed. So far, I'm doing well, but it's mainly because my house isn't suited to orchids because a lot of orchids need more humid conditions. And so I can do the Phalaenopsis quite well because the Phalaenopsis is what is most commonly sold around here, like Walmart, Target. And that's because it's bred for the normal person to keep alive and have it flower and successfully flower. And so this is a little bit more hardy. And then you get into some of the more specialized orchids that they need often it's pretty humid conditions. And so I have this one from this left one called the chocolate orchid, and it literally smells like hot chocolate in your house when it's blooming. It's just wonderful. You walk in and you just be hit with this wonderful hot chocolate smell through the day. And then at night, it goes down. In fact, when I went to purchase it at the local flower shop, it was around 7 o'clock at night. And I got it home and unwrapped it. And I, went to smell it and there was no smell. And I got all indignant. They sold me a bum plant. It's not smelling like chocolate. Oh. Well, then the next morning when my alarm went off, I'm like, what's that smell? I mean, it was through the whole house and chocolate. So that was like, oh, okay. So it's only during the day that it does that. Probably a good thing. So hungry at night. But beautiful, beautiful orchid. But it wasn't happy in my house. I had to donate it to the greenhouse. Actually, it's still in there. Years later, it's still going, even though it was near death when I donated it, because it really does need a lot of humidity. So that's what it looks like. I purchased one, huge flowering space like that. Very delicate, beautiful flowers, as well as the wonderful scent. So it is pretty easy to get obsessed with these, but like I said, you have to know what you're doing and you have to really research your plants because if your home or apartment doesn't provide suitable habitat, they won't do well. They'll flower. You'll probably purchase it in flower, and then you may never get it to flower again because if your home's not well suited, it won't flower. Okay, so in lab, you'll be watching toward next week, maybe, or the week after. We'll ask you to watch a video by Sir David Attenborough, and he spends a lot of time talking about orchid pollination strategies, and they are pretty famous for duping or tricking their pollinators without giving any reward back to the pollinator, and they have evolved amazing adaptations to attract the pollinator, but not really provide much of a reward. Some do, some provide a reward, but many don't. So you'll get to see that in lab. We'll ask you to watch that. Okay, the basal angiosperms, I'm not going to spend much time on. Just mention a few things. So when they say basal, they're talking more ancient. They're closer to the base and are still, there's some species still in existence. They haven't gone extinct. They're just more primitive. Water lilies, we have those around here on inland lakes in particular, Nymphaceae family. And if you are canoeing or kayaking, you might go up to one and you'll look and you'll see that there are many flower parts. Again, that's a more primitive design. Here's another one, Amberella. Again, lots of flower parts. They're unusual because they don't have vessels, so really primitive. If they're not showing vessels, that's pretty unusual. And some botanists say they're most closely related to the earliest angiosperms that are still living. You can still find these; they're still living. They haven't gone extinct. And then the magnolids, including magnolia and pepper, where we get black pepper from. So those belong into the basal angiosperms. So some are, so when you're looking at these ideas, especially zooming in on the flower and flower design for looking at what's more primitive, what's more advanced. And then here, just looking at the evolutionary timeline, We're looking at the Devonian period when the seed plants. So when, remember now, when we say seed plants, that includes gymnos and angios. Okay, so don't forget about the gymnos. So that's about 365 million years ago, and about 142 million years ago in the Cretaceous. That's when you start to see the angiosperm fossils. So the gymnosperms came first. This table shows it a little bit better, I think, here. And now this is kind of going through all the different plants we've been looking at, all the way down to algae. So you see at the very bottom here, the Precambrian time, which is 4.6 billion years ago. Vascular plants diversify during Silurian. I'm not going to be asking you to memorize all of this. I just wanted to show you that they have pieced this together pretty well. Here you see the seedless vascular plants during the Carboniferous. We mentioned that one. That I would like you to know mainly because that's the time when we start talking about the dinosaurs. And really, if you're a botanist, you'd say it's the age of the seedless vascular plants, not the age of the dinosaurs. And then you start to see the gymnosperms popping up during the Triassic. But by the time the Triassic and Jurassic, we had a lot of seedless vascular plants, and then the gymnosperms start popping up. And then you see it's not until the Cretaceous that you have the angiosperms. And then you can see they're tracking where the pollination players are showing up. So they're tracking this pretty well through the fossil record. Very painstaking work in order to piece it all together. And you can see we don't show up to quite a bit later. Now, there has been a lot of debate about where certain crops evolved and where they're native to. And this is going to change a little bit. But one thing I'd like you to think about and kind of appreciate is that we've thrown away the idea that crops originated in just one spot of the world. We see that crop diversity, the origin of different crops, is actually quite diverse across the globe. It's not just in the Mediterranean, but that was one of the short things. But you can see here in this map, of course, showing crops, but you can see across the globe you have the different crops that are currently grown still today. Of course, I do research with potatoes. That's what I did for a postdoc as well. I studied potato, and there was all kinds of argument in the literature about where the potatoes originated from. But just fairly recently, they all finally agreed, okay, yep, it's in the Peru region of South America. So different areas of the world, you can find where they cultivated those particular crops originally. When you look, I mean, this could be a whole semester class in and of itself. When you look at crops and the history of that, how they're been manipulated over time to give us our current crops that we grow. Wheat is a good example. That one had a amazing history, and it's mainly two grass species that were hybridized. And there's several regions of the world where that was being bred. And so with most of the crops that we have today, it's lots of heavy human intervention where you do a lot of breeding. You like the traits of this plant, you like the traits of that plant, so you try to get them, you know, the pollen from one to the stigma of the other and see what you get. Rice has been the same way. They think it's at least 3 separate times it's been domesticated in regions of Asia. Of course, Asia is big. And that's another huge crop that is so important for feeding, you know, billions of people. On the left, that is the more wild relative of corn on the cob. That's teosinte. And if you kind of look at it and squint, you can kind of see the corn on the cob idea. And so the progression of this domestication has taken many rounds of human insight to go from that to our current corn on the cob. There's been some interesting articles that have been published in the last several years. You know, with such heavy human intervention, when we do these types of breeding, selective breeding, we're usually trying to breed in traits that will sell well and make a profit, right? Which is understandable. You know, I get that. The problem is that they didn't always think about the consequences. Like if you, so like corn on the cob, one of the traits that sells well, people will buy, is sweetness. We like really sweet corn. We don't like that more starchy taste. And so sweet corn sells really well. And there's a paper published about the idea that as they were breeding for sweetness in corn, they inadvertently bred out resistance to pathogens. Accidentally, I mean, they didn't do it on purpose. But there's this type of idea where there's consequences, even with the best of intentions, there can be some consequences. And so the idea here is we can be a little bit more thoughtful about how we go about breeding for crops. And then the other thing, kind of amazing, we have so few plants that we use for food. When you think about 250,000 different angiosperms, and really there's so few of them that we actually use. Here's a fun one. Look at what we get from wild mustard. So all of these cabbage, broccoli, kale, kohlrabi, Brussels sprouts, all of them, that's all being derived from wild mustard. They took it in selective bred until they got these different crops that we see today in our stores. So when you eat broccoli, you're eating flowers. Those are flowers. Well, cauliflower has the word flower. But a lot of people don't know broccoli is actually flowers too. That's how I got my sons to eat it. You're eating a flower. Go ahead, try it. At least they tried it once. So wonderful crops that we're getting through this process of domestication over time. Grasses are unique. They have very unique flowers. I'm not getting into the anatomy, but I've had students ask in the past about grasses, and you have to really look carefully. Grass flowers are pretty nondescript, not fancy, and often they're kind of hidden away. But if you're curious, flowers in the grasses do occur. They just don't look like a whole lot. And then there's tiny, this is the world's smallest flower. Okay, this is a duckweed plant. And so these are actually the anthers. That's the anther there, stamens, tiny. Okay, and then the last couple slides are just for fun. I'm not gonna ask you about these, but I've had students ask me about orchids, and this is kind of fun historical facts about orchids, but I'm not gonna ask you about that on the exam or anything. All right, we gotta stop there. We'll get into flower and fruit on Wednesday.